Okay, so let's get started. We are going to continue our discussion of virtualization, wrap that up, and then hopefully start a new topic, which is still on processes, so it's going to be process migration. But just to go back to what we were talking about last time, I got some questions about hypervisors. So I just wanted to do a recap and then also re-emphasize some things that may or may not have come out very well. So as I was talking about two types of hypervisor, if you remember, there's a type 1 hypervisor which essentially runs on bare metal. Essentially it's going to just run on a machine. There's no other OS below it. You can have a number of virtual machines that run on top of a type 1 hypervisor. Here is a light gray virtual machine that essentially is running Windows. To Windows, it just looks like real hardware. It's emulated hardware, but the Windows operating system here doesn't know that. It just believes it's running on hardware, and then it has its own application. Here's a darker Linux virtual machine. Linux runs, and then apps run on top of it. And you can have a number of these on any hypervisor. This is a type 2 hypervisor, which presumably, if you have used any virtualization techniques on your desktop or laptop, that's probably what you've used. So you have your regular operating system that you are going to run, whether it's Windows or Linux or Mac OS X, or then your virtualization layer is essentially a regular application. Okay, whether it's VMware or Parallel Desktop or VirtualBox, it's just an application that you start up. That application contains a type hypervisor, which we call a type 2 hypervisor in this case, that runs a guest. So you can have, again, a number of virtual machines that run on top. Okay, so here is one that is running an operating system. Okay, called, in this case, we call this a guest operating system. The native one is called the host operating system. Okay, so there are two. There's a regular OS that runs on your machine, okay, and then there is a guest OS. Okay. So that's basically the two scenarios. Now, last time after I spoke about this, some of you came and asked me if there is a type 1 hypervisor running, where did the OS go? Okay, where is the operating system that you would normally expect to boot on a machine? So the clarification I wanted to provide, which I briefly alluded to last time, is there is no operating system. Okay, when you power on a machine, it's the hypervisor that boots up. Okay? In other words, a hypervisor is essentially a special purpose kernel. Okay? Whenever you boot a machine, you boot up a OS kernel on that machine. Okay? There is no regular operating system here. Okay? The hypervisor essentially performs all the tasks that are entrusted to a kernel. So it's a special purpose kernel. In fact, that's how it is typically built. Okay? Early versions of VMware, which is a commercial hypervisor technology that you can buy. Okay, so they essentially took Linux. Okay, they took the Linux kernel, they stripped out the unnecessary or the general purpose feature, and they essentially made a special version of Linux that only supported virtualization, no other features that you normally expect in a general purpose operating system. So if you booted up that hypervisor, essentially you are booting this very special purpose, highly modified version of Linux. So there was no real OS, that's the OS. Okay, that's the thing to keep in mind. Is that clear? Any questions on type 1 or type 2 hypervisors? Okay. So I'm going to continue our discussion. I talked about type 1, type 2, paravirtualization and so on. And this is where we had stopped last time. So everything we have talked about so far relates to CPU, okay, the processor and how to virtualize the processor. A typical virtual machine needs to emulate all the resources on that machine. That would include the memory, the disk, the network, and so on. So I'm going to give you a little bit of a glimpse into how other resources are virtualized. Okay, CPU, we said you could do emulation, you could do native, and all of those things. So here is memory. Okay, so essentially, you have RAM. Okay, on your machine, this is native RAM. Okay. You have partitioned some part of RAM and allocate it to a VM inside, and then when the OS runs, there are processes that run on that VM and so on. Okay, and, inside that piece of memory. Now, what happens as far as back to the picture here? So you have hypervisor. Let's say you have an OS and you have applications here. So the OS has to manage memory for its application, like any normal operating system would. Okay, so that would include managing the page tables that track what parts of memory are allocated to which processes. The page table is a data structure that does that. So now, so the OS has kept track of these page tables for each process. Whenever it's modifying the memory allocation for the process, it has to modify the page tables. Okay? But modifying a page table is a trusted operation. It's a sensitive operation. Okay? Because it requires, page tables typically use hardware and TLV support and so on. So an OS would normally need kernel level privileges to make those modifications. Now, as I said last time, the hypervisor is the trusted entity on any machine. The operating system that runs inside the VM is not. So it wouldn't actually be able to modify those page tables itself. It needs to use the hypervisor to do it, make these changes for it. And so the way this is going to work is the hypervisor keeps an extra set of page tables, which we are going to call shadow page tables. Okay, so there's essentially a copy. Okay, so whenever the OS is going to try to make changes to the page table, it's not going to be able to do so. It's going to cause a trap, okay, like we talked about last time. We're going to trap into the hypervisor. The hypervisor is going to figure out some changes are being made. It's going to use the shadow page tables, which are essentially a replica, and make those changes, and they get reflected in the main page table. Okay, so this is essentially how you are going to be able to manage memory, okay, or make changes to memory allocations of processes, even though the OS doesn't have the rights to do it. Okay. So it's not very different from what I showed here last time. Whenever the OS is trying to make any execute any sensitive instruction, it causes a trap. Okay. Modifying page table is also a sensitive operation because it requires you to make changes to hardware, and the OS is not the privileged entity here, is the hypervisor. So the way you deal with memory and page tables is through this notion of shadow page tables, where there are virtual pages are mapped to the VM's physical pages, and the hypervisor is actually going to change the mappings. Essentially, it's a two-level mapping. There's mapping that's maintained at the OS level, but there are shadow page tables that reflect the actual mapping. Okay, so that's just an example of how that same idea we talked about last time can be used here. Okay, so let's move on to I/O virtualization. So in this case, you are trying to virtualize the disk. Okay, the disk is essentially storage on a machine, and there will be multiple virtual machines. Each is going to get some storage resources. Okay, and you want to virtualize the disk. So as far as the OS inside is concerned, to it, whatever storage is being provided should look like a real disk, even though underneath how it's realized is up to the virtualization layer. Okay? Now, typically, the way you do this is when you create a new virtual machine, you create a virtual disk associated with that virtual machine. The virtual disk is going to store all of the code and the data for that VM, including the OS and all the applications and their data. Okay? And whenever the OS tries to access the virtual disk, the hypervisor is going to then go to that storage object and provide access to that virtual disk. Now, typically, the way virtual disks are implemented is they are actually files in the underlying file system. Okay? Your OS is going to have a file system. Inside the file system, you create large files. Okay, so if you have seen VMDK files or things like this, they are actually virtual machine disk files. They're virtual disk files associated with the virtual machine. And then essentially that entire file, okay, it's actually a file underneath, looks like a disk inside the virtual machine. Okay. So I'm going to show an example here. Okay, so you can get some sense of what this looks like. So here is VirtualBox. Let me just start. Okay, so that is your. So if you look at this, you will see that that's the set of files that the virtual machine maintains in the file system, and there is a VDI file which is a virtual disk image. Okay, for Ubuntu, you'll see that it's a very large file if you look at the size of the file. Okay, so essentially, as far as the file system is concerned, there's a very large file, okay, which is acting as a virtual disk. Now, if you go inside the virtual machine, that file actually looks like a normal disk. Okay, so if you look here. Okay, so you'll see that this just looks like a regular file. Okay, it has partitions and it has a file system that's layered inside the virtual disk and all of that. Okay, so as far as the virtual machine is concerned, it looks like it's reading or writing from a normal file, but underneath the virtualization layer has mapped that to a large file on the file system. Okay, so you're essentially taking a file, the storage space in the file, and making it look like a disk to the virtual machine. Okay. And whenever you read or write to a location on the file, you go to the appropriate location on the disk, and when you try to write to an appropriate location on the file here, you go to the corresponding location on disk and read or write there. Okay, so if you have a 2 GB disk, there'll be a 2 GB file underneath that's acting like the disk. Okay, yes, question.
Does VMware allow that we can break this 2 GB file into multiple partitions?
Okay, so questions: can VMware allow you to break the 2 GB file into multiple smaller files? So you can have different ways to implement a virtual disk. Okay, you can create one gigantic file, okay, of arbitrary size, and that can act as a virtual disk file. Now, in certain file systems, there are maximum file limits. Like if you have a fat file system, there's a 2 GB limit on the maximum file size. So if you try to create a virtual disk that's greater than 2 GB, you can't make one file that's bigger than that. So what you will do is you'll break your virtual disk into smaller files, part 1 of the file and part 2 of the file and part 3 of the file. Then your VMDK file will be broken up. Now, if you have a file system that supports larger files, you do not need to do that. That's just because underneath the file system may be an older rudimentary file system.
If it is broken, like 2 GB files, then can I create a 4 GB file in the virtual machine?
Yes, even if you have 2 GB files, the virtual disk is the collection of those files. So it appears like a single disk that has a storage space that's the sum of the file sizes. Right? So if you have 4 2 GB files, and so the logical view and the physical view are different. So you might have a logical view of a 8 GB. So this is a logical view of a 8 GB disk. Okay. Now, as far as the virtual machine is concerned, it can realize this by, let's say, 4 2 GB files on the file system. Okay. And so that essentially means that the first quarter of the virtual disk is stored here, and the next quarter here, and so on. Or if your file system so supports, you can make a big 8 GB file, and then this would just have one-to-one mapping. So how you implement it is up to the virtual machine. Okay. Any other questions? Okay. So we need that. Let's move on to. So that's I/O virtualization. So we talked about how to virtualize disks, how to virtualize memory, how to virtualize CPU. You also need to virtualize the network, okay, or the Ethernet card or the Wi-Fi card. And the way typically that's done is you have this notion. Let's say this is a machine. It has an Ethernet card. Okay, that's an Ethernet interface. Let's say it's called ETH0. If you have a virtual machine here, okay, that's running on this machine, it will be given a logical network interface, okay, called a logical NIC. Okay, so again, it's an emulation of an Ethernet card. Okay, so this will be, let's say, a logical interface, and this logical interface is simply mapped onto a physical interface. Okay, there may be more than one of these. Each virtual machine is given its own logical Ethernet card, okay, or it could be some other network card, and they are all mapped onto the physical interface. So when The application here sends out a network packet. It comes to the logical NIC. The logical NIC is going to hand it to the physical Ethernet card, and it's going to be sent out. When a packet arrives, the Ethernet driver has to figure out who the packet is for, okay, and then forward it to the appropriate virtual machine, and that virtual machine is then going to process it and give it to the application. Okay, so if you look at a typical when you start up virtual machine, if you look at the underneath the interfaces, you'll see that there will be logical interfaces that are created that are simply mapped onto the physical interface on the machine. Okay, is this clear, or is there any questions? Yes.
Do they use different ports, like how different applications use different ports?
Okay.
Is it some other way?
The question is how do you use ports and whatnot? So the way, as far as the processes inside are concerned, they do not actually know what is going on. Okay, they just assume that that's the actual Ethernet card on the machine, and they send it. So you could still have, let's say, an HTTP server here, which is going to listen on port 80. Okay, so port 80 on this Ethernet port might actually map on. It's not the same as port 80 on this machine, because there may be actually a port 80 in use. So you have to map this to whatever the physical interface is doing. Okay, so there are the equivalent of NAT mappings that you are going to use. So you can still have your own port numbers inside the virtual machine. When you send out packets, you have to do a translation saying this has its own IP address. Okay, you are going to translate that to the IP address here and send it out. When the packet comes back, you have to figure out that this is actually meant for it and send it out. So you are going to have to do both an address translation and a port might have to get translated if you are actually exposing the port. Okay, because you can't have two VMs using the same port. That's you have to have it unique for a machine. Okay. Yes.
Is there any implement to design to schedule these logic code network cards?
Is there a way to schedule the logical network card? So that's a good question. In fact, that question can be generalized and said, how are you allocating any resource? How are you scheduling any resources? Okay, whether it's, if there's a CPU, how are you scheduling the VMs? Is there a network card, how are you scheduling the VM? So I'll talk a little bit more about this when we talk OS virtualization, but there is a scheduler. Okay? If multiple VMs are sending out packets, you have to essentially allocate a portion of the bandwidth to each of the virtual machine. So if this is a gigabit Ethernet card, you can say 100 megabits is given here and 100 megabits is given here, and then there's a scheduler here that's going to enforce the limit. Okay? So you can say if packets come from two VMs, you have to schedule them in a certain order so that you fairly allocate the resources here to each of the VMs. Okay? Same is true of the CPU. Okay? If there's a one core here, you have to schedule the VMs like you're scheduling processes. Okay? Each VM will also get scheduled in the same way. Okay? So it's the hypervisor's job now to do scheduling of resources for virtual machine. Just as an OS schedules across processes, the hypervisor schedules resources and allocates them to virtual machines. Okay? The same analogy is true. Any other questions? Excuse me. Close your laptop. So that's basically as far as scheduling is concerned. I will talk about OS virtualization, okay, and we'll talk about scheduling in a lot more detail then. Before I move on, are there any other questions about hardware level virtualization? So finished one layer, okay, which is the hardware. We are going to talk about OS and very briefly talk about applications. Okay. So now the early use for a lot of these virtual machines were not only the ability to take a server and create smaller virtual servers and run application in them, but it was also a way to distribute larger applications. So you could get things what are called appliances. Okay? So which was essentially a fully packaged virtual machine that has an OS and some application in it. So rather than downloading some application and configuring it, you could just download a virtual machine, okay, which is pre-packaged as all of the OS and application built in, and you could just run it. Okay. So you can actually go to the VMware website and there is a marketplace there, okay, which you can download an appliance that has a pre-packaged version of many complicated distributed applications. So you don't have to get several pieces and install them. They're all done. You just get the virtual machine and you start it up, everything is already been installed inside the virtual machine for you by the developer. Okay, so you don't need to go and redo all of the installation yourself. Okay? So it became a way to distribute software. Instead of getting a CD and then installing the software and then spending a lot of time configuring that software on your machine, somebody's already made a virtual machine. Okay? They have installed the software inside the virtual machine. They have done the configuration or the default configuration for you. So all you need to do is now download the virtual machine and run it, and the software starts running with the default configuration, which you can change. But a lot of the work of installing complicated software is all gone. Okay? So that is basically was one use. So virtual appliances were a good use case that made virtual machines popular. Okay? Today, this has evolved into Docker containers. Okay? So Docker, if you used it, will do the same thing for you. In fact, I'll show you some examples where you can get prepackaged software and inside a Docker container, which is a lightweight virtual machine. It's an even easier way to distribute software. Okay? So a lot of software is now getting distributed as containers. Again, you do not need to download some binary and then install it and configure it. It's all installed inside a Docker container. You can just download a lightweight virtual machine and run, and it's all set. Okay, so I'll show you some examples of that after we talk about OS virtualization. Okay, so that brings us to the next topic, or subtopic within virtualization, which is what is OS virtualization, how does it work, how is it different from hardware level virtualization. Okay, so here is an example of OS virtualization. Okay, so you have your regular hardware. Okay, you have an operating system that runs on the hardware. And remember, when we talk about OS virtualization, we are now virtualizing the system call interface. You can emulate one system call interface using the other, or you can provide an emulation that makes it look like it's an older version of the kernel, or even if you want to just do isolation, you can emulate the same interface but give isolation. Okay? So you have your OS, okay? And here are the applications that run on the machine. Normally these applications would run as normal applications. They would compete for resources, and they would see one another. One process can see other applications that are running, look at all the files and so on. Now if you want to provide some degree of isolation, you can create what is called a container and run the application inside the container. Okay? What that will do is then the application can only see processes that run inside that container. It does not see other processes that are running on the machine. Okay? So also you can allocate resources to containers, saying this container can use no more than 10% of the CPU on the machine. Okay? It can use no more than 200 megabytes of RAM or whatever you can specify resource limits. Okay? And the OS is then going to enforce those limits for the container. Okay? So it's a way to provide isolation. Okay? You can isolate this process from other processes of the system. You can provide resource limits so that the process does not take anything more than whatever you have allocated to that process. Okay? Now, if you think about it, virtual machines also provide this isolation. Okay? When you create a virtual machine, you can say give it so much memory, give it so much resources, and so on. Okay? But the way virtual machines work is if you had a virtual machine rather than a container, you would have to first run an entire OS inside that virtual machine and then run that process or application on top of the OS. So it's a lot more heavyweight. In hardware virtualization, you need to run an OS inside the VM before you can run the process. Here, you are not actually running any OS inside a container. So you just have your regular OS. That regular OS provides you a container support so that it can give you this isolation without any additional software or OS that needs to be installed. Okay? So many would call this a lightweight virtualization technology because you do not need to have multiple kernels running. There's only one, okay, which is your regular machine kernel. Okay? So that's an example of containers or OS level virtualization. Okay, now that's in this case, these applications all see the same OS underneath. Okay, so they're going to see the same system call interface. So you're not emulated any new interfaces in this case. This use case is simply for isolation. Okay. Here is another example of a different operating system called Solaris. Okay, that's Oracle's Unix operating system. It has a OS virtualization technology called Solaris resource containers. Okay? They're called RCs, or Solaris containers for short. In this case, you can create what are called zones. Okay, and a zone is essentially the same as a container that I talked about here. But you can also say that in this zone, pretend like you are this OS. Okay, so essentially the system call interface that is presented to a processes inside that zone could be different from these other zones. Okay? The simplest case is you can say, if this is, let's say, OS version 10, you can say inside this zone pretend like you are this kernel version 9. Okay? So now this is an old application that was designed to run on version 9 of the kernel. It will continue to run even though in version 10 maybe the system call interface has changed. Things will not break. You don't need to port the application. You can just say that inside this zone, pretend like you are an older version of the kernel. And so each of these could have a different kernel version. You could of course say pretend like you are a different kernel altogether. In that case, you have to re-implement the system call interface using the native one. Okay? Some containers might do that, but the simplest use case is where you have backward compatibility. Okay, so these are just examples. Now, every operating system now is coming up with this support for containers. In BSD, it's called jails. Okay, this container is called a jail. So you essentially jail a process, and then you cannot see what's outside the jail. You don't get a limited set of resources. That's what you can use. Okay, Linux also calls it containers. The newest version of Windows, okay, which is I think Windows 2016, which is not yet released, it is going to have support for containers as well. Okay? Because this is lightweight and it's become very popular. Most of the commercial operating systems as well as the open source one are providing this support out of the box. Yes, question.
So this is to prevent the applications from interfering with each other, right? But wouldn't they still be able to write, for example, to a file and then the other one reads from that file?
Okay, so that's a good question. I will talk about this in more detail. So the question is, isn't this for one application from interfering with another application, and could they not just trample on each other's file? Okay? That depends on how you will configure the container. I'm going to show you different ways by which you can isolate even the disk. Okay? And just to be clear, resource isolation is only one advantage of container. In fact, the reason things like Docker have become popular is not because you get isolation, but because of a lot of the software engineering advantages you get, because you can develop code, you can put it in a container and you can ship it, and your users of your code will see the code exactly the way you shipped it. They don't need to configure. So package distribution has actually become even more popular than isolation. This is a technical benefit. That's a usability benefit. Okay, so we'll talk about both. Yeah.
So in both hardware virtualization, we had a logical layer of everything, right?
Yes.
From the Ethernet to memory to.
Yes.
But so in this OS virtualization, I mean, what do the containers? Are they a layer between the OS and the applications, or like?
The only layer, there is no layer. The containers actually run on the kernel. This is just a way to isolate them. Okay. Having said that, you can still construct new network interfaces and say this container only talks to this interface, or it only uses this core and so on. So you do get those benefits. You can create logical network interfaces and attach them to a container. Okay? That's because the OS itself has the ability to construct logical links. So you can simply use that and say this container can only send using this logical link and provide isolation.
No, I mean, like, when I create a container, what does that mean?
So when you create a container, all that means is you have your own kernel running, your own OS running. Okay? And when you run this application inside the container, you start a process and say it's inside this container. All that is happening in this case is this process can only get resources that are associated with this container. So if you say no other processes are visible, and inside this container you go and you do top or you list all processes, you won't see those other processes. Okay? Or you can say restrict the file system inside this container to only these directories. So this process will not even see other files that are on the disk. Okay? So the OS essentially blanks out those things for the container. Okay? So let me describe how they work in a little more detail. Maybe that will answer those questions. This is just high level, what is it used for, not how it works, right? So we'll talk about how it works. Is there any question? Yeah.
So what are the advantages of package distribution with respect to containers?
What are the advantages of package distribution? Let me finish let me finish talking about Docker. Then I'll show you some examples that is going to answer that question for you. If it's not answered, you can ask it again when I talk about it. Okay, because that's coming in 3-4 slides. Okay, so here is some technical advantages. I already mentioned it provides resource isolation. Because they're lightweight, they're much faster to create. Okay, so to create a normal virtual machine, you have to first install an OS on that virtual machine. That's going to take some time. You can just create a container and then run a process in that container. It's very fast because it's much more lightweight. There's nothing to install in there. Okay, you are just essentially saying this is a container and this is the resources allocated to it. You get native performance because there's no translation. It's just a way to provide isolation. Okay, so your processes are actually running on your native OS kernel. Okay, they're just isolated from other things. So there is no slowdown in any sense. Okay, and it's lightweight. Okay, and this picture, which probably is hard to see, okay, shows you the difference between type 1, type 2 and containers. Okay, this is type 1 hypervisor. Okay, you will see that's hardware, there's hypervisor running, there's a VM, which probably is hard to see, but it's the same picture I showed you. This is type 2 virtualization or type 2 hypervisor. This hardware, that's your host operating system, that's the hypervisor, like VirtualBox. Okay, then there are VMs running and there's another OS running here, two kernels. Okay. Here you have the hypervisor and a kernel. Okay. Here there's kernel, hypervisor, another guest operating system. Okay, that's the picture for a container. You'll see that all you have is hardware, you just have your regular OS, and then essentially you have this gray box that's a container to which you allocated certain resources, and the OS is simply enforcing those resource limits for you. Okay? And the process is just running inside the container. So there is the number of layers is reduced, so you should see that the overheads have gone down. It's a lot more lightweight than either of these two. Okay? More software layers you add, the more overheads you're going to have. Okay, so it's more lightweight, okay, and that's the picture that you should keep in mind. Okay. Now let us talk a little bit more detail as to how some of these techniques work. Okay, so we'll talk about three. Okay, one is called namespaces that provides you process level resource isolation. Then there's actual resource isolation where you can set limits on the CPU and also prioritize how much CPU you get, how much network you get, how much RAM you are allocated. Okay. You can change the root directory, and I'll explain what that means. And you can have other security policies that says this container can only do certain things, or this port is blocked for this container. If you have an untrusted application, maybe you can say that block all these network ports on this container, but other processes can continue to access them normally. So if the process tries to access some ports, it's blocked from doing that. So you can have different policies for different containers. Okay, so let's talk about each of those. Okay, we'll start with the namespaces. Okay. So what does the namespace mean? It restricts what a process can see. Okay, so this is global level isolation of resources. Okay. So in some sense, if you are running a process inside a container, it's given the illusion that is the only process in the system. Okay. So if it tries to do PS or top or list all the processes running, it does not even see other processes. Even though they are running, to that process they are not visible. Okay? So you can only see certain processes there. Okay? You can also restrict file systems. So you can say that this container can only, let's say, so this is your root file system, maybe your /user. You can have home, where there are home directories, and then you can have. So this is your. Okay, so this is your file system tree. Okay, and you can say that to this container, you can only make this subtree visible. Okay, so if these files are not even visible, so if you try to cd /user, the process tries to do a CD for /user, is going to get an error saying that directory doesn't even exist. So it's like you see a restricted version of your disk. Okay, some files, some directories can be made invisible. Okay, you can see you do not have access to it, so they cannot even see those. Okay? They exist on the underlying file system, but the OS just makes them invisible to the process. Okay, so if you try to access them, you get an error as if they don't exist at all. Okay? But underneath, regular processes can continue to see them like usual. Okay? Only within the container you can restrict them. Okay, so that's what this is. That you can have restriction on the file system, you can have restriction on processes. So it goes without saying, if you cannot even see some processes or see some directories, you can't go and muck around with them. You can't say if there's a virus on this, it can't go and attack some other processes because you can't even see them. Okay, so we'll get more isolation and more benefits. So and then you can also restrict which users are even visible. So inside this container, maybe only certain users are actually visible. So if you try to log in or try to access something belonging to other users are not even visible. Okay, so you can restrict every resource that's visible. Okay, you can say what a container can do or cannot do. Okay, you can have policies on all of those resources. It could be user IDs, it could be passwords, it could be file systems, it could be processes. All of those can be restricted. Okay? And that is called a namespace. A namespace is what named resources can this container see, whether the named resources are files or they are processes and so on. Okay? Questions on this? Okay, so that is namespace isolation. And then the other thing that I should mention before I move on, that this is how Linux implements container. These are what are called Linux namespaces. Every OS is going to provide some similar set of features, but we're essentially looking at Linux containers as an example of OS level virtualization. But the concepts are general. Okay? But I'm just presenting them through the lens of whatever Linux is actually going to do. Okay? So the other thing that you can also do is resource isolation. Okay? So those were resources like processes and so on. This is just saying what hardware resources can you use. So you can set limits saying you only get to access 10% of the CPU, or only core 1 and core 2 is accessible to this container, core 3 and core 4 are out of bounds. You cannot schedule any processes there. So then to this processor, it look like it's a 2-core machine. Okay, so you can do that. So that's CPU sets. You can say this is the set of CPUs a particular container can access. Okay, the picture is here, which is not very easy to see. These gray boxes are all the hardware resources, and the green, red, these are containers, and the arrows say what are you allowed to use, what is limited, and so on. Okay, so you can limit RAM, okay, you can limit IO, you can limit the CPU, and so on. Again, similar to what you could do in virtual machines, but now you're doing it in a more lightweight fashion. You're just telling the OS, when you schedule this container, ensure that it doesn't use up more than 10% of the CPU. Or when you try to allocate RAM to processes in the container, ensure that you do not give it more than half a gigabyte. That's the limit. If you hit the limit, even if you have free RAM, do not allocate. Okay? So you're just telling the OS saying, enforce these restrictions. Okay? So then it's going to have to make it work with the underlying schedulers, whatever CPU scheduling or memory allocation policies are inbuilt, those will have to respect those limits, okay, which normally wouldn't be present. Is that clear? Any questions? Okay, so that's C groups, and I'm going to go into a little more details as to how you can enforce these limits. Okay, so I'm going to talk about a specific scheduler that's going to implement a limit of this sort. Okay? Now, if you remember what we talked about maybe 3 classes ago, we already saw one scheduler that could actually do this, which was lottery scheduler. Okay? We said if you do lottery scheduling, you can allocate a certain number of lottery tickets to, in this case, it would be to a container, and it's going to get allocated CPU in proportion to the lottery tickets. Okay? But lottery scheduling is a randomized scheduler. Okay? It requires randomization. There are deterministic schedulers that do exactly the same thing. Okay? And a class of them is referred to as proportional share scheduling. Okay? This is widely used in many different virtualization scenarios. So I'm going to introduce in one slide what this is. Okay? So What is proportional share scheduling? Essentially, in proportional share scheduling, you allocate a share of a resource to a process, okay, or to a group of processes, and the scheduler is going to ensure that it is going to get that share. The simplest way this is implemented is through this notion of a weight. Okay, weight is very similar to a lottery ticket. Okay, so you can allocate a weight which is an integer to each process I. Okay, and that process is going to get resources in proportion to its weight. Okay, so essentially, if you have, let's say, 2 containers, okay, and you are given this a weight of 1 and that a weight of 2, this is going to get a third of the CPU share, and that's going to get a 2/3 of the CPU share. This is why it's also called share-based scheduling. Okay? So the normal abstraction is you essentially have a weight and you're allocated that resource, in this case it's the CPU, in proportion to your weight. Okay? And the way you can think about this, the simplest way is if you have weights and your time slots, you can say this has a weight of 1, you're going to give container 1, container 2, container. So a very simple way of implementing shares. Okay, so now first time slot is given to this, the next 2 time slots are given to this, and you cycle back. Okay, now every third of the CPU goes here, 2/3 goes here. Okay? The actual schedulers do something more sophisticated than this, but this is the basic intuition. Okay? Now, there may be many specific things that a share-based scheduler has to deal with. Okay, what happens if you're given this container 2/3 of the CPU, but when the scheduler, the underlying CPU scheduler tries to schedule this container, all the processes are idle. They have nothing, no work to do. Okay, no process is ready to run. What should be done then? Where should that time slot go? Okay, so let's take this very concrete example. Let's assume this is your red container, okay, and that's the black container. Okay. This has a weight of 1, that's the weight of 2. Okay, so the way you are essentially going to schedule them is you're going to allocate this time slot to red. This one goes to black, which doesn't work. Pretend that's black. That's the best I can do. Let's make it green. Okay, so this goes to green. Okay, then the fourth one is again going to go to red, green slot, and so on. Okay, so these are time slots. So you give one first time slot here, then the green time slots go here, and this one. So you'll see that you're given a third of the time slots of CPU time to red container and 2/3 to the green container. The question is, when the CPU scheduler says this is the time slot allocated here and there is nothing to run there, what should you do? Okay. That's a question every scheduler will have to answer, because you have to figure out what would you do, because you have specifically allocated a share. In the best effort scheduler, you never do that. You just look at your ready queue and whatever is on the queue gets scheduled. You're not explicitly allocating a certain amount of time. Here you have to perform this allocation. Okay, so then you have to ask, if I am not able to use something that's allocated to me, what should be done to that time? So there are only 2 answers. Okay? One is you say that's a time slot belonging to the green. If it doesn't want it, let it stay idle. Okay? Then the time slot just goes to waste. Okay? The other thing you could do is saying, this, you get the time slot, but if you don't want to use it, you give it up, then it gets reallocated to some other container that's willing to use it. Okay? So those are the 2 types of share-based schedulers you will actually see. Okay? If you have what's called a fair scheduler, it is going to take unused cycles and redistribute them to other containers in proportion to their weights. Okay? So if there are more than one, let's say there was a different colored container here, if there are idle time slot that green is not using, you're just going to take them and allocate them in proportion. Okay, so if there are 2, so every unused time slot is going to be split between them, or you're going to alternate between them and reallocate. Okay? That is what is referred to as a fair scheduler. Okay? Another example, which is hard limits, is you say that your time slot belongs to you, and you can use it or you can let it go waste. It's your choice. Okay? But we are going to do that strict allocation. Okay. Now, So those are called hard limits. So you assign an upper bound and say you can use it. It's not going to be reused by anyone else. If you don't use it, that's going to go to waste. Okay, third policy is you redistribute, but you basically keep track of your unused time, okay, in the form of a credit. Okay, so this is essentially you're going to allocate a credit to each container, and they're going to accumulate credit. This is like your rollover plan that cellular companies have. Right? So you don't use your minutes, they will get added to your account. You can use them in a subsequent month. Okay? Same is 2 year. Let's say you get two time slots every second. Okay? You don't use it, that's fine, but you will keep adding to your balance. Okay? At some later point, if you have a IO or CPU bound application that needs a lot of CPU time, you can just draw down from the credit, saying I accumulated so many credits, now I'm going to start using them. So when you are accumulating credits, your time slots may be given to someone else. So someone else is benefiting even though they haven't actually not asked for them. But when you start using your credits, they might come at the expense of someone else's time slots. Okay? So you're going to balance in that fashion. So there are many different policies a share-based scheduler could use. In this case, the first of the 3 cases, you redistributed unused cycles, but you don't accumulate a credit because it's a use it or lose it. If you don't use it, you lost it and it's given to someone else. Okay? But you can't come back later and say that time slot that I didn't use, I want to use it now. Okay? That concept is not there. It's just fairly allocating whatever you do now. In the hard limits, if you don't use it, you actually let it go waste. And in a credit base, you can give it up, but then you are given a credit that you can reuse at a later. So all of these are actually policies that are implemented in real systems, and I'm going to show you some examples. So if you look at Linux-based schedulers, they actually use share-based schedulers. Okay, so there's a scheduler called BFQ. This is also called fair queuing, incidentally. Okay, so if you in the networking literature, okay, these schedulers are called fair queue. Okay? In the OS literature, they are called proportional shared scheduler. They mean the same thing. Okay? They just have two different terms that mean the same thing. So you will see that there's something called BFQ, which is some fair version of fair queuing scheduler, which as of last week they replaced it with another one called CFQ. So these are all news, the articles that are posted to the Linux kernel mailing list. Okay, saying I made a new scheduler, I'm going to submit it for review or something along these lines. So you will see that these are actually implemented in Linux or other equivalent operating system. Okay? And the credit-based scheduler, you may not be able to read this, but the credit-based scheduler is actually used in cloud computing servers. Okay? You can get servers, which in this case they are called burstable instances, okay, in Amazon's terminology. They are given a certain number of credits an hour. Okay, like if you buy a cheap one, you may be given 6 credits an hour. If you don't use it, if your application is idling, you can accumulate those credits. So at some later time, if you have to do a burst of work, you can draw down from your credits and you can run at full speed. Okay. So the credit-based scheduler, so you'll say each instance receives CPU credits continuously. The rate depends on the instance size. And when they're idle, you accumulate. And then when they're active, you can essentially draw down from your CPU credit. Okay. So all of these actually are being used in some shape or form in virtualization world. Okay. Cloud computing only, so basically all uses virtualization underneath. So they're implemented the same ideas.
Can you game the system with this? And say like, I'll give this up so that later on I can run it at full speed.
So this is something I actually meant to say here. Okay, what exactly the question you asked, saying that one risk of a credit-based scheduler is you accumulate a lot of credit, okay, and then say I want to burst. So now I have 1,000,000 credits, so let me run for the next so much time, and you starve out other processes because you have more credits. You are going to be given priority. So one risk of a credit-based scheduler is that you can actually starve out other processes. In fact, this was the very first share-based scheduler that was designed. And people said, we don't like it, it causes starvation, so let's do that. Okay, so you don't use, you basically lost it, you don't get a credit. So, but both variants exist, and they can cause starvation. Or you can cause problems by accumulating credits and then saying, I have a long burst now, some other process starts. Any other questions? Alright, so that share-based scheduler. So that's essentially a glimpse of Linux containers. Okay, it basically has its namespaces, it allocates resources, you can specify limits on the resources. Underneath, the OS has to implement more sophisticated schedulers that's going to implement all of these features, waits, or hard limits, or accumulate credits, and so on. Here, this picture you don't have to worry about, it's complicated. But now, having talked about that, let me talk a little bit about Docker. Okay, what is it and how does it work? So essentially, Docker is a technology that's built on top of Linux containers. Okay, and what it allows you to do is it adds a number of additional features. So underneath you have Linux containers, but it adds portability. So you can create a container on one machine. You can then hand over the code for that container or the image for the container. You can run it somewhere else. Okay? So you get portability. And the reason this is important is for software distribution. A developer can write their code, they can test it once it's all ready, rather than giving you a CD or a tar distribution. You essentially ship your product as a container. Okay? And your customers will just download the container and run it. So you don't need to reinstall anything, okay, or configure them. Okay? This is adding an application-centric view to containers. Everything we looked about was from OS up. We said, what do you have to do in the OS to make all of this work? Now let's think from application down, saying, here's an application. Okay, I built it, I want to send it off. How do I do it? Okay, so it has a complete tool chain that says, here, take the code, package it as a container, here's a repository, upload it to the repository, tell your customer they can just go to the repository, they can download it, and they can just run it. So there's an entire tool chain that makes it very easy, okay, to distribute code. It makes it easy to build new versions of your code, update your repository. So the repository uses Git. Okay, you're distributing your entire containers using Git-like repositories. Okay. So there are all these additional software engineering advantages and tools that Docker has included. Underneath, the technology uses containers. When you take a Docker application and run it, essentially it runs inside a container. Okay, so I'm going to show examples. So here's a picture before I show an example. So that was your container, and essentially Docker adds a runtime and some software engineering tools on top of that. But from an OS standpoint, it just looks like a normal container. Okay, so with that, I'm going to show pictures here. Let me see. Okay, so here is a graphical view of Docker container. So what this is just a GUI, and it's showing you all the various containers you can download. Okay, so which are available as in the Docker repository, and you will see there are many. Okay, here is PostgreSQL. Okay, so if you need Postgres database, rather than downloading Postgres distribution, installing it, all you need to do is just click create. It's going to download it. It will appear as one more container here. You just say run and it will just start running. Okay, very simple. Okay, and then you will see that practically every large piece of software is available. I mean, this is just a few that they show. You can just search for whatever you want, MySQL, you can search for Apache, you can search for all sorts of software that are now being distributed using Docker containers. Okay, so now I should show you one more thing here. So if you are actually thinking how this is going to work, I said that this was built on top of a Linux container. Okay, but this is a Mac. Okay, it's running in OS X. So you can say, why is this even running on this machine? Are you running this on a Linux machine? So actually I am not, but I created a Linux virtual machine on this in VirtualBox, and this Docker is running inside a Linux VM. Okay, that is why I can even make Docker work on my Mac. Otherwise, I would need a Linux machine. Okay, and just to show you, you will see that this is the Linux VM that's running on VirtualBox. Okay, inside this VM, I'm actually running Docker, and that's just a GUI that is talking to that VM inside. Okay, this is just one way to run Docker on a Mac. Normally, you would have to run it on a Linux box. Okay, yes, question.
There's just a clarification on how containers work, right? So now you have these applications that come in their own separate containers.
Yeah.
But didn't you say that containers are used for isolation of applications?
Yes.
So if you had to use it with another, say you wanted to use Postgres,
Yeah.
but you had some other application you want to use it with, how would you kind of?
Okay. Question is, that's a very good question as to if you have downloaded one container and you want to make it work with another one or have it talk to another application, how would that work? I was actually going to show an example here, which is, I don't have Postgres, but I have MongoDB, which is another database. Okay. So I could run this is come as a container. Yeah, in fact, I'm going to start it just so that you can see what's going on. So you'll see it as a shell and it's going to show you that it ran and rather you'll see that it became green. So it's actually running here and I don't know why the log doesn't show up, but I can even open a shell. It might work or may not work. Okay, so here is the shell prompt that I got. So now that's the shell prompt on the inside the container. Okay. Now if I do a PS here, okay, which actually is not even allowing me to do PS, but let's say okay, so this is highly restricted. It's not even letting me list processes, let alone look at the processes. But if I actually was allowed to do PS, I would only see that application, which is MongoDB. I wouldn't see anything else. Okay. Now you asked a question. Let me get back to your question. Now you say I downloaded this database, it's running in its own container, but I actually wanted to talk to a web server. How do I do that? Okay. So the way you can do is you can take containers and you can hook them together. You can say this container can talk to that container on this port. Okay, that opens up a channel that allows two containers to talk. They are normally isolated and they can't see each other, they can't communicate. But you can take all these containers and hook them together. Once you hook them together, they can actually talk using whatever channel you created for them. So I could then install a web server, which I can try if it works. This is just a web application. And let's see if it does anything. So this web application actually uses MongoDB as its database backend, and there is some code there that we have hooked together, and it should actually do something, but I'm not sure whether it's doing anything at this point. Okay, but that's the answer to your question. Okay, so now at this point, the other thing I should mention is actually it didn't start. Let me see if I can start it. Okay, so something is wrong. It's not configured properly, probably. Oh no, this is the one to start. Okay, so anyways, I'll make it work next time if you want to see. Right now, but that's the short answer to the question as to how to make all of this work. Okay. So that is just a quick glimpse of Docker, okay, just so that you have some sense of how OS virtualization works. Any questions before we move on? Yes.
Yeah, Prof, I still haven't answered the question. The package distribution with
Yes.
the advantages.
What are the advantages of doing this? As I said, the advantages is the user doesn't actually have to download, install, and configure, right? So I could just, you can just take this example, right? So let's see. That is not what I wanted. So if I go back to this page, okay, so if I want to download one of these database things, I would just have to say create, and the entire package is coming to me as a container, and I just need to say run, and then the application starts running. Normally, if I had to give you a package, you would have to install it, okay? Then you would have to go and change all sorts of configuration files, you would have to read a manual, and then you would get it to run. Here you don't have to do anything because it is pre-configured for you. So it makes it much easier for the end user to start using complicated applications. This is only valuable when your applications are complicated. A simple application, you wouldn't do this for a browser, for example. There isn't a whole lot of configuration involved. But all of these like databases, web servers, they all require you to do lots of configuration. So it makes it easy. Okay, yes,
To add to that, Docker uses a layered file system, so
Yes.
you can easily build upon containers to extend their functionality, which is quite different from
Yes.
virtual machines of old.
So I didn't mention some of the additional details of what Docker does. It has a special file system, Union FS, which will give you benefit. But that's not important for understanding virtualization. That's important if you want to use Docker for something. Okay, so that is it as far as this is concerned. Okay, so I said, okay, so you can have run once, deploy anywhere, you can pull images, you can keep it up to date because it's just sitting in a repository, you can update your containers and so on. Okay? And essentially the question that was asked was, how do you use containers? So they are called microservices. If you actually go search for web microservices, these are essentially containers that have smaller applications and you hook them together to make a bigger service. Okay? So that's essentially how Docker, in the Docker world, envision how you will take containers and use them together to build a larger distributed application. Okay, yes.
Do you have like a system call or an interface for which you call commands for each container, or do you have access to the internal structure of it?
So there's going to be a homework on Docker where you will actually have to do this. You will get an answer when you figure this out. But the answer is yes. There's a Docker command line interface. So you'll say Docker and you can do various things. You can say start and stop and create, and it's a whole set of commands that allow you to manipulate containers or start them or hook them together and so on. Okay. All right. So let us. Okay, there's actually one more slide here. So we are now going to go back one level up and just talk about virtualization in general. We've done with the OS level, we're done with the hardware level. So here is where, not how it is used, but where it is used today. Okay. Virtualization is widely used in cloud computing. Okay. If you use any cloud platform, underneath they are using some form of virtualization to make virtual machines, to give you virtual servers. No cloud provider actually gives you a physical machine because they have to manage it. They might have to take it back from you and so on. If you own the machine, they can't do that. So they control the hypervisor and they give you a VM and you can run your application inside the VM. So cloud computing is one area where it's used widely. It's also used widely in data centers where you might have large servers with lots of cores. Many applications may not need to use all of those resources. Okay, if you buy a 16-core machine and you want to run a small application, it doesn't need 16 cores. So what you would rather do is you would create a container or a VM and create a virtual server and say, let me run 10 of these virtual servers. Inside each I can run a separate application. Okay, and it just looks like I have 10 individual smaller servers. They are all running on one bigger server. Okay, this is how data centers work. So they use what is called server consolidation, where they take older machines as they retire. Rather than buying one new machine for every old retired machine, you buy one bigger machine and it has presumably more cores, and then you take lots of older machines and you take their application and run them on a single new machine. The way you do this, you create one VM for each old machine, and whatever was running on that old machine now runs inside the VM. And because this new machine is a lot more capable, you don't need all of the resources. A fraction of the resources is going to be the same as whatever was on the older machine. Okay? So you can consolidate older servers by packing multiple old servers onto a newer server and using virtualization. Okay, you can also use it for desktop environment. This is testing code, developing code, and so on. Virtualization is used. If you want to test a code rather than getting a machine to test, you can get a virtual machine, run your test, and then stop it. Or to do development, you can use the same kinds of ideas. Okay, so you can do Linux development on a Mac by just having a VM on Linux, and you can then test your code, for example. Okay, so many different uses of how for virtualization. And that is where we will stop the topic, not the lecture. The lecture is going on for another 15 minutes. And so here is, so we are going to switch gears, but before I go to process migration, which is the next chapter in the book, I want to mention a few things about server design and how you design large-scale servers. Okay, I briefly alluded to some of this earlier, but I put together a small set of slides just to make that clear. Okay. So we talked about client server already, okay, when we were talking about architectures. Okay, and so typically you have this request response paradigm where client makes a request, server processes the request and sends back a reply. Okay, typically the client has to figure out where the server is running, what port is it listening on, and so on. If you have well-known services like HTTP, you know that the server will be listening on port 80. But if you design your own service, you might have to tell the clients where the service is running. Okay, that is typically done through what is called a directory service. Okay. We are going to talk about directories and naming in chapter 4, which is coming in a few slides, but because lab 1 is going to be given out in a little bit, we might have to make these design decisions before we even talk about some of this material. Okay, so how does the client locate the server? You can hard code the address of the server, or you can register the server to a directory service. The client contacts the directory service and says, what is the credentials of the server? The directory service will tell you where the server is. Okay, that's a standard way for a client to locate the server. Okay, just keep that in mind. But let's come to some other design issues. Okay. Whenever you have servers, there will be many things you'll have to decide. Is the your server stateful or stateless? Is it going to be a multi-threaded server? Is it going to be a multi-process server? Or is it going to be event-based server? So many different design decisions to be made. Okay? And there will be implications on many things like performance and other things on how you design your server. So let's take some of these issues and try to go into them a little more detail. Okay? So typically a server could be stateful, in which case it keeps track of what active sessions are going on. I mean, when a user connects to a server, you start a session. Okay, let's say it's an online store. Your browser, you connect to your store, and then you may be browsing. You may put something in a shopping cart and so on. So all of that is the state of that session. Okay? The server has to keep track of that state. If you say, now let me check out whatever is in the shopping cart, the server needs to know what is it that you actually put in. So all that becomes part of the state. Okay? So in this case, some applications make the server stateful. Okay? The server has to keep track of every active user session. Okay? There are other servers that will have a stateless design. Okay? They keep track of no state at all. All the state is maintained at the client side. Okay? So you can even implement this notion of a shopping cart by using a stateless server. The way you would do this is you will take whatever you put in the cart, you would encode that into a cookie and send it off to the browser. And then when you say checkout, the browser has to present the cookie so that the server now knows what you put in the cart. Okay? So you can encode a state and keep it at the client. So you can design servers in a stateless fashion as well. Okay? Most servers that you will design probably for your lab and whatnot are going to end up being stateful. Okay? But there are many advantages to a stateless server as well. Okay? For example, if your server process crashes and recovers or restarts, okay, all the client state which is kept in memory is gone. Okay? If you kept the state of the shopping cart into a memory data structure, it will just disappear. Okay? So the only way you can actually recover from failures is either the state has to be kept on disk, which is going to slow things down, okay? Or you keep it at the client, which means it becomes stateful and the client crashes. Server crashes don't impact the client. Okay? So it is more resilient to failures, a stateless design. Okay? It is more scalable because there's less work to do at the server. The client takes over some of the burden. Okay? So there are many pros and cons to whether you go stateful or stateless. As I said, in many cases you might just go with a stateful server and not worry about some of these things. But if you're designing a complicated application, these decisions actually matter. Okay? There's a third in-between approach which is called soft state. Okay? So by soft state, what we mean is the server is going to keep track or cache some information on behalf of the server, on behalf of the client rather, and keep it for a limited time. Okay, losing soft state does not impact correctness, okay? But keeping soft states improves performance. It's like caching. Okay? You can cache some data, okay? And having something in the cache accelerates your performance. But not having it doesn't impact correctness. It just takes you longer to get to some data item. Same concept in a different way is soft state, saying rather than me, I can keep a cache of what is in your shopping cart. Okay? I also send you a cookie so that the definitive state is kept at the client. Okay. Now, if I for some reason I want to discard whatever I've cached, that's okay. I can ask the client and it will supply me all the information. And if I still have it, I don't have to ask the client. I can just do local processing. That's an example of a soft state. This arises a lot in networking where routers keep track of soft state to do routing and so on, okay, instead of keeping hard state. The hard state is problematic because any crash means loss of state and then there is a problem. Okay. So this is an in-between approach between stateful and stateless. So essentially, it's a stateless server that caches some state and discarding it does not impact correctly. That's the way to think about it. Okay. So these are all different ways to design a server from whether you keep state or not. Okay. Just one axis for design. Okay. I'm going to talk about a couple of others. Let me come back to this. Let me talk about server architecture. Okay. The other decision you are going to have to make is what process level architecture are you going to use. Okay. Are you going to use a sequential server? Are you going to use a concurrent server? Are you going to use concurrent threads or concurrent processes? Or are you going to use what is called an event-based server that uses asynchronous? Okay? So there are 4 choices you have. Okay? In a pure sequential server, your server only processes one thing at a time, a single threaded. Okay? To accept a request, it will process it, it will send a reply. If any other requests have arrived in the meantime, they will be queued up. So then you go take the next request. So you just sit in a loop and say accept a request, process a request, send a reply, accept the next request, and so on. So you just have a simple loop. The simplest kind of server you can build. Okay? Not the most effective one, but the simplest one. Okay? Now, thread-based and process-based server both add concurrency. Okay? You have more than one thread or more than one process available to service request. Okay? So more than one request comes in, you can hand them to individual threads or individual processes and say go process them concurrently or in parallel. Okay? So then each of these slave threads or slave processes is going to go do the processing, send back a reply. Okay? So these are two architectures that are going to give you more concurrency than the pure sequential case. They are more complicated because you have to have either a multi-threaded or a multi-process system with synchronization and communication between the components, etc. So going from here to here gives you lots of benefits, but code is going to get more complicated. And then the last one you have is what is called event-based. I put it in the middle, but it's event-based. It is a pure sequential, but it is non-block. It uses non-blocking I/O. So essentially, a one thread, and it's going to process, let's say, a request. But if the request does I/O, it doesn't block. It sends off a non-blocking command and says, let me go and process other things in the meantime, rather than waiting for that process to the request to finish. So you pull up the next request and you start processing. And whenever any I/O finishes, you get back interrupt. Then you go into an event handler or an interrupt handler and process that request. So that's another way you can take a single-threaded process, but yet get some notion of concurrency built in because you're using non-blocking commands to implement your server. Okay? So those are 4 architectures, okay, for server design. Okay? Now very quickly we can talk about which one is most efficient from many different scenarios, okay, in terms of throughput, in terms of system overheads and so on. Okay? So let's ask ourselves which one might be the least efficient from a performance standpoint. Pure sequential should give you the least throughput because you are processing exactly one request at a time. And if that request happens to block or does any I/O, it needs to read a file, the server is just going to wait for it. Even though other requests have come, it doesn't process anything. Okay? So from a throughput standpoint, it's going to give you the least throughput. Okay? All of these other 3 provide you some degree of concurrency. Okay? Multiple requests, outstanding requests can be processed. Okay? Here they will be processed by multiple processes. Here they are going to be processed by multiple threads. Here they are going to be processed by the same thread, but the thread is not blocking. It will take the first request, do some partial processing. It does I/O, it switches to the next request. Okay? While the I/O is ongoing, it will go process the next request, do some partial processing. The first request finishes, it will switch back, process it, and then switch back to the second. So it's going to do this using event. So it's going to give you some notion of concurrency as well. Okay? So all three will give you higher throughput than a sequential. Okay. Now, if you try to say how do you order these three, okay, they're all going to give you concurrency. But now let's think about overheads. Which of them will have higher overheads or lower overheads? Okay, so let's look at these two. Which one do you think is going to have higher overhead than the other?
Processes.
Okay, it's process based. And why is that? What overheads do you think are incurred? Okay, clearly it seems like it should have higher overhead. You have more processes here, just threads. Okay, but what are the actual system overheads you're going to incur?
Switching the process means switching the page tables.
Okay, context switches are going to be expensive. Okay, when you switch from request 1 to request 2, you have to actually switch processes. That's context switch. That is expensive. Here you are switching threads, which is much more lightweight. Okay, that's the first overhead. Second overhead is this is going to consume a lot more RAM than this, because you might have 10 processes here. Each is going to take an entire amount of RAM that's allocated to a process. Here, all the threads share the same address space. So this is going to be more heavyweight, both in terms of its RAM usage and also from context switching, because switching between threads is more lightweight than switching between processes. Okay. So that's the ordering. We said this is the worst. These all have concurrency between these two. We ordered and put this before that. Okay, this is better than that. Now what about this one? How does it compare to the other two? Event based. Okay, so you can ask which one takes more memory. Will an event based server take more memory or a thread based server take more memory?
Maybe thread based because you have multiple threads.
The thread base is going to take a little more, but it's kind of a wash because they just still take a single address space. This is just a single threaded process. This is a multi-threaded process. Still only one process. Within a process, you have more threads, so it may take a little more. Clearly, these two will take much less memory than that because here you have multiple processes. Okay, so there may be a slight advantage to an event base, but not much. Okay, from a memory standpoint. What about context switches? Just others overhead, right? There are two overheads, RAM and switching.
Maybe event-based is best because thread-based they need to. There are context switch between threads, but no, there are only one thread in the event-based.
Okay, so what is just suggested is event-based is going to be more efficient because there's only one thread. Here you have multiple threads, you have to switch between them. Here there is nothing to switch, there's only one thread. If there's work to be done, that thread is just going to continue. It is the one that is just calling functions to say, let me process request 1 versus request 2 and so on. Okay, and that is indeed true, and that actually is a substantial boost for performance. Okay? This is context switching between processes, heavyweight. This is context switching between threads, less heavyweight than that. Here there's no context switching at all. Yeah, there's only one server, there's only one thread. So if there's work to be done, you will basically just continue to run this server. So as it turns out, what this discussion will also tell you is the most efficient servers you can build actually happen to be event-based servers. So if you want really care about performance, okay, you are going to go for an event-based architecture. It's also by far the most complicated to build, okay, because writing code for event-based servers is a lot more complicated than writing threading code. Okay, threading code itself is more complicated than a single process. This is even more so because you have to write event handlers, you have to handle interrupts, and so it makes your code much more complicated to design and debug. Okay, but you will see that the most efficient ones happen to be this. So if you go and look for, go and search efficient web server, okay, you will find that the ones that you will pop up are things that will actually run an event-based architecture. Apache, which uses a thread-based architecture, is very popular, but by no means is it going to give you the best performance if you care about performance. Okay? And the same is true for any server you write. If you really care about performance, that's the way you will have to go. Okay? Most of the time, you won't care about it that much that you'll take the trouble. You'll probably go this way or this way. Okay? Sequential is not the most ideal design choice. Yes.
Which one of them is most CPU intense?
Okay, which one is most CPU intensive? Okay, I think the CPU intensity is going to depend on how much request you are processing. The request processing is going to be identical for most of them because you just have to execute certain code to process the request. Okay. So the only other thing I will mention is if you have multiple cores, okay, this ordering is going to change for you because event-based cannot take advantage of multiple cores. So this ordering is only true for if you're running on one core. Okay? Because these two are true concurrency. They can actually get true parallelism and run these processes or these threads on multiple cores. These two are actually sequential. They can only run on one core at a time. So in a multi-core system, the ordering will change. Event-based will actually do worse because it cannot even run on the other cores you have in your system. Okay? But if you have an event-based server, what they will do is they will actually start a 4 event threads if you have 4 cores, and each one of them will do event processing. Okay? But that's a very complicated hybrid model where you're threading and event-based. Okay? That's even more complicated to get. Okay? So that's basically the ordering. So this is something to keep in mind. It's something you might actually come up with when you think about design. I'll talk about this slide and leave or stop because we are over time. So this is just a slide that shows you how you can get performance by having replicas. Okay, so you can do what I said in the previous slide, which is have processes or threads and get concurrency, but you are still bound by the capacity of your machine. Okay? You bought a quad-core machine. At the end of the day, your capacity is determined by how many cores you have. If a lot more requests come in than the capacity on those 4 cores, the only thing you can do is actually go across machines. You actually then run your server on more than one machine. Okay? That is called clustering. Okay? Clustering is just a way by which you take a server, run it on more than one machines, and have them work collectively to present the notion of a server. So whenever you have clusters, you have what is called a load balancer or a dispatcher sitting in front of it. Requests come in, they are forwarded to one of the, in this case, 3 machines, and then each machine is then going to go and do its processing of that request. So this is a load balancer. It is taking the incoming stream and splitting it across the cluster. Okay, and then each machine in the cluster does its own processing using a process-based or a thread-based or an event-based architecture. Okay? So this is essentially then going and taking it and making it truly distributed. Whatever we talked about previously was not distributed, a single machine. Okay? So this is how you build a really high-performance server. You will then actually distribute it across machines. Okay? So let's stop here. We are over time, so we'll continue this next time.